Several experimental values are determined by taking several samples of the parent population and calculating their means. The values of these means, they are supposed to be close together, but not exactly the same. However, the distribution of these values is normal in nature and can be studied. For example, let's say that we want to study the average grade in statistics 2 in Cambridge assessment throughout the globe in a given year. We could do this by using several samples, which in this case would be the grades that each school, for example, would have. We would pick a given number of schools scattered around the globe, determine or get the value of the grades for statistics 2 in that school, and get the mean for each school, and then study the value of all these means, which would be normal in nature, and make an assessment of what the overall mean would be globally based on these individual means. The point is that we are assuming here that the underlying population, that is the population of all students taking statistics 2 throughout the globe, is normal in nature. But the point is that besides that, the distribution of the means of all the different schools, the grades in each individual school, the distribution of all these means is also normal in nature. If we take here the orange, as being the normal distribution of the underlying population, okay, all students globally, the distribution of the means of all the schools that we've picked as samples would also be normal in nature, obviously around the same value, the same mean, okay, but much shorter. The curve would be much shorter. Why? Because the parameters are going to be slightly different. As you know, for the normal distribution, as you've learned last year, the parameters are these. But for the distribution of the means, here you would have the variance divided by n being the size of the sample, which in this case would be the number of students for which you're calculating the mean in each school, which should be the same throughout the globe for this study, okay? In some situations, the population mean and the standard deviation or the variance cannot be given and must be estimated from a particular sample, okay? Not in this case, but there may be situations in which it is impossible to get the mean of the parent population. So we make an estimate of what that mean might be based on the information that we get from a certain sample. Obviously, the estimated population mean is going to be given by the formula that you are used to since, well, ever. But for the variance, you have to use this one. No need to memorize it. It is part of MF19, so you might as well use the MF19 if you ever asked to calculate unbiased estimates for the population variance. Just go there and get it. Okay, now that you know this, we can talk about the hypothesis test for the mean using the normal distribution, okay? To test whatever hypothesis for the mean using a sample distribution, okay? So in the example that I gave before, it would be the sampling distribution of all the means for all the schools that we used as samples, okay, given by this. And a particular sample mean, we need to know and set up all these things. First, we have to establish what the null and the alternative hypothesis is. Don't forget what we are doing here. In a hypothesis test for the mean, we make a claim, H1, that is the alternative hypothesis, about the population mean, and use the sample mean to test whether the observed difference is small enough to be explained by random sampling or large enough to provide evidence against the null hypothesis and towards the alternative, okay? This is what we are testing, and each question that you are going to solve is going to propose a testing like this. Sometimes has to be you, the one proposing the test. Okay, so you obviously need the null and the alternative hypothesis. That's where everything starts. You will have to have a significance level against which you are going to make and test the hypothesis. And you have to look also if it is a one-tailed or two-tailed test, because this is going to influence on the calculations that you are going to use. Then you have three methods to use, and you can go ahead and pick your own. I have one of them is a third one, just because it's much simpler, but you use whichever suits you best. The first one is using the critical regions, okay? So again, don't forget what you are testing, all right? So what are you going to do? You are going to use the significance level of the test, here represented by S, to determine the z-value associated with it, okay? If you have a one-tailed test, you are going to determine the value of z, doing first 1 minus the significance level, and then use MF19 to get the value of z. You already know how to do this since last year, I think. If you have a two-tailed test, don't forget to divide the significance level by 2, so you can get the value of z, okay? Then determine the critical value. Once you have the value of z, the critical value is determined using this formula that you already know as well, all right? Don't forget that you already will have this value, and that value. So you determine the critical value. Establish then the critical region or regions, depending on you having a one-tail or a two-tail test, okay? And then, to finally test the claim, you are going to locate the sample mean on this distribution to either accept or reject H0. Again, if it is in the rejection region or regions, you are going to reject H0. If not, you are going to say that there is not enough evidence to reject it, okay? This is one way. Another way, using probabilities. So in this case, you are going to calculate the probability that the randomly chosen sample mean, okay, is smaller or bigger than the sample mean under study, okay? So in this case, let's say that you are suggesting that the population mean is smaller than a given value, pre-established value. And you are going to use a sample mean to test that, okay? If we calculate the probability of any other sample mean to be smaller than the one that you have, and if you say that if you, after calculating it, you see that this probability is big, then there is not enough evidence to suggest that H0 may be rejected. You see the point here? So the procedure is this. Here I put for smaller or bigger, depending on whichever situation you may have. If it is smaller, you are going to calculate the probability using, well, the way that you know since last year, using the normal distribution. And if it is bigger, you just do 1 minus that. You already know that, okay? And once you have a number over here, you are going to compare with the significance level. If the probability is bigger than the significance level, then H0 must not be rejected. Only when the probability that a random sample is smaller than the one that you have, or bigger, depending on the situation that you are studying, only when that probability is small are you able to reject H0. Okay? Last one is the simplest one in terms of calculations, is the one I use more often, is using critical ratios. So the first thing is get the significance level of the test and determine the z-value associated with it. Already is the same thing as over here, okay? And then you are going to calculate the z-value of the sample mean, okay? What is the z-value of the sample mean? It's also called the critical ratio. It's going to be the observed value minus the expected value. Actually, sorry, it's going to be the absolute value over there. If this yields a negative number, just make it positive. So this works always, all right? This is called the critical ratio. Then what you do? Compare the two z-values to either accept or reject H0. If this one is smaller than the one associated with the significance level, then H0 is not rejected. If this one is bigger than the one associated with the significance level, then H0 is to be rejected.